In this video, you're going to learn quadratic functions. Now, in other math courses, you've learned about linear equations. You remember a linear equation is y equals mx plus b, can be written in that form. So the equation of a line might be given by an equation like this, y equals 2x plus 1. These things produce lines. Or you could go y equals negative 4x plus 3, and it would be something like that. Those were lines. We're going to take a look at, in this video, quadratic functions. So instead of the x just having an exponent of 1, like these ones do, what if we looked at the function y equals x squared? And so when the variable x has an exponent of 2, that's when we call them quadratic functions. So quadratic functions are functions like y equals x squared. Let's see what this graph would look like if we graphed y equals x squared. So if I'm going to graph y equals x squared, one of the things we could do is we could make a table of values. So we could pick some values for x and some values for y. And I'm going to pick a few of them that are close to 0. So I'm going to pick minus 3. Now when I put minus 3 in here for x and I square that, that's positive 9. And when I put minus 2 in here and I square it, that's positive 4. Minus 1 in for x, negative 1 times negative 1. When we square that as 1. Put in a 0. 0 times 0 is 0. Put in a 1. 1 squared is 1. 2 squared is 4. 3 squared is 9. So now if I'm going to plot these points on my graph, if x is minus 3 and y is 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, whoop, right up at the top here. If x is minus 2, y would be 1, 2, 3, 4. And when x is minus 1, y is 1. When x is 0, y is 0. When x is 1, y is 1. When x is 2, y is 4. And when x is 3, y is 9. So clearly, it's no longer a line, but rather the quadratic equation, whoops, let's try that again, try to get her through that point. And this would continue to go up. So we'll put little arrows on here to indicate this is going up. So the graph y equals x squared looks something like this. And we call this shape of the quadratic function, we call it a parabola. Okay, we call it a parabola. Now we also have access to graphing software. And so we could also enter the graph y equals x to the power of 2 into the graphing calculator and have it draw it for us. And again, we get the quadratic equation. So here's a couple of different examples of parabolas. So this has that parabola shape. And you can see, some of them could open up, some of them could open down. We could have lots of different pictures or different shapes of the parabola. And so what are some of the properties that we have of the parabola? Well, this little point here that occurs, in this case at the bottom, and this little point here, we can kind of call it the pointy part of the graph, is what we call the vertex. And the vertex is just a point, so this would be the point 2, 1. Over here, the vertex would be minus 1, 4. So we can talk about the vertex of the parabola, and that's sort of that corner point. Now sometimes that corner point, or that little part of the bump there, will be a minimum, or sometimes that'll be a maximum, depending on whether it opens up. So if the graph opens up, like this one does, opens up like this, then we would say this graph has a minimum value at y equals 1. So y equals 1 is the lowest y value of this function, and since it goes up forever, there would be no maximum. No maximum value here. No maximum y value. Over here, because this one opens down, well, then we're going to have a maximum. And what is the maximum? The maximum is y equals 4. This graph doesn't get any higher than 4 on the y-axis. But because it goes down forever, there would be, obviously, then no minimum. And you'll notice that since the shape of these graphs are parabolic like this, that the domain for all of these functions, that's all your x values, is always all real numbers. So the graph goes to the left forever and it goes to the right forever. Same thing over here. This graph will go to the left forever and it'll continue to go to the right forever. So the domain will be all real numbers. So the only question is, what is the range? And of course, if this opens up, then there would be a minimum value of 1. So we'd have y values greater than or equal to 1. And over here, since we have a maximum value of 4, the range would be y less than or equal to 4, because all the y values below 4, you can find points on the graph. The other thing that we can talk about when we have a parabola is an axis of symmetry. And so this little green line here we call an axis of symmetry. And it's kind of the imaginary line that we would draw right down the middle of the parabola that makes the graph symmetrical. So if I took the right side here and folded it over to the left side, this part here would line up on this part here. So I've kind of split the graph right down the middle. That's what the axis of symmetry is. And it has a very easy equation. Remember, any vertical line is going to have the equation x equals, and then we just got to figure out what the x value is. Well, we've got that from the vertex. So the equation of this vertical line is x equals 2. All of the points on this vertical line have an x value of 2. So the equation of the axis of symmetry would be x equals 2 on this graph. And over this one, the equation of the axis of symmetry would be x equals minus 1. So once you have the vertex, all you got to do is find the x coordinate of that vertex and say the equation of the axis of symmetry shall be x equals minus 1, or x equals 2. And that's covered virtually all of the properties of the quadratic function. One other thing that we could talk about is we could talk about the x and y intercepts. So remember, the x-intercepts would be here's the x-axis, the place where the graph crosses the x-axis. So in this left example here, the x-intercept would be none. There is no x-intercept. It never crosses the x-axis. But it does have a y-intercept of 1, 2, 3, 4. So the y-intercept would be, where does this graph cross the y-axis? This is the x-axis and this is the y-axis. So this would have a y-intercept of 4. Now in this example, if we're asked to find the x-intercept, you can see clearly there would be 2 of them, but the x-intercepts are not going to be integers. So the only way we can do this from this little picture is to approximate them from the graph. So this looks like this might be about 3.3. And over here, this might be minus 1, minus 2, minus 3, 4, 5, maybe minus 5.5. And the y-intercept, again, we're going to have to approximate it. 1, 2, maybe 3.7. So we can approximate the x-intercepts and the y-intercepts from the graph. Now, if we actually had the equation, which we don't here, but if we had the equation, then we could use algebra to find the x-intercept and the y-intercept. So what we'll investigate now is what what do we have to do to that original graph? Remember the original one that we did, y equals x squared? What do we have to do to what do we have to do to this equation? Sorry about that. The screen has a mind of its own here. What do we have to do to this equation y equals x squared to get these graphs moving all over the place and flipping up and down, opening up, opening down? This one's kind of skinny, this one's a little bit wider. Let's investigate what we can do to that equation to produce some of these different graphs. So here's the graph y equals x squared, and I got my little table of values down there, and I've sketched my graph. What if we started to play around with the number in front of x squared? So right now this is like a 1, y equals 1x squared. What if we did this? What if we did y equals 2x squared? We put a 2 in front. Well, we could do a table of values here, and let's stick with the same ones. And if I put negative 2 in here and I square it, I'd get 4. But now I've got to multiply everything by 2. Well, that's going to make that 8. And when I put negative 1 in here and I square to get 1, oh, these should have been 1. My mistake here. 1 squared is 1. I drew the graph properly, but didn't have the table of values properly there. So negative 1 squared is 1, but 1 times 2 would be 2. And if I put 0 here and I square it, I times it by 2, I still have 0. If I put 1 in here square to get 1, 1 times 2 is 2. And if I put 2 in here, 2 squared is 4, 4 times 2 is 8. Well, when you compare these numbers to these ones, the y values are twice as big. They're 2 times bigger. And so when I plot these points, negative 2, 8 is way off my screen here. Negative 1, 2. 0, 0 is the same. 1, 2, and 2, 8. Let's see if I can go back up here a bit. There we go. 4, 5, 6, 7, 8. 8. So what have we just done? We've just stretched this graph vertically by a factor of 2. So all of the y values twice as big. We've stretched it. What if we did something like this? Y equals negative 2. What if we made that a negative? Well, we could do a table of values again. We could put in, let's do the same ones. When x is negative 2, negative 2 squared is 4, but now we have to multiply 4 by minus 2. So this is going to be minus 8. And the effect of that negative is all of these values are going to be made negative. So now when x is minus 2, we've got 1, 2, 3, 4, 5, 6, 7, negative 8. And when x is minus 1, y is minus 2, and 0 is still 0. And 1 is minus 2, and 2 is minus 8. And so the blue and the green graph look identical. 2x squared, 2x squared, same shape, but what did this negative do? The negative sign just reflected in the x-axis. So it now opens down. So if you want a parabola to open down, make this number in front of x squared, usually we call that a, make that number negative. Well, instead of manually graphing all these other ones, because we still haven't really seen, what if we made that number in front of x squared less than 1, like a half? Maybe you'd think, well, no, okay, maybe now all my y values are half of these ones. Let's see what happens. We can do this on this graphing calculator. So here's the graph of y equals x squared. a, that number a there, is going to be this number in front of the x squared. So y equals ax squared. And we're going to just see what happens as that number a changes. So right now it's 1. It looks like the regular parabola. If we made it 1.5, you can see the y values are now 1.5 times bigger than the original graph. And if we made it 2, here the y values are twice as big. So there's the 1.5 again. There's the 1. Now what happens if we make a half? That's exactly what happened. Now this new graph, the y values are half of what they used to be. And then this is 0, which would just be a straight line and not a parabola at all. And here's negative a half. So the negative is going to flip the graph in the x-axis and make it open upside down. And the half is going to make the y values half of the original ones. So here's negative 1. So when a is negative 1, we get the reflection. And the y values are the same as the other graph, just negative. And then there's negative a half, and there's negative 2. So the larger the value of a, the skinnier the graph will get. And when it's negative, we have a reflection in the x-axis. So to summarize here, if we have y equals ax squared, we've now found out that a is going to control the shape of the graph. So if a is more than 0, so if this is a positive number in front of x squared, the graph is going to open up like all of these ones do, positive 2, positive 1, positive a half. But if a is less than 0, then the graph's going to open down. So here a was negative 2, this graph opens down. And then we found out that if a is more than 1, the graph's going to be narrower than y equals x squared. So the blue one here would be y equals x squared. Y equals 2x squared simply means that all the y values have been doubled. So that makes the graph appear skinnier or narrower. And then if a is between 0 and 1, so it's a fraction in other words, like a half, y equals a half, then the graph's going to be wider. So we get this one like this red one. And what's really happened here is all the y values are half of what the original ones used to be in y equals x squared. So that's what happens when we muck around with the coefficient of x squared. We get these, we can change the wideness or how skinny the graph is, and we can make it flip upside down. Okay, so what if we tried to add something to the end of this function? And usually we denote that to be, use the letter q, so y equals x squared plus q. Let's add 2 to the end of this function and see what happens. Let's do a table of values and put them in and see what happens. So here we're going to put negative 2 in for x, square that, that's 4. 4, but now we got to add 2 to it. So 4 plus 2 is 6. And if I put negative 1 in here and square it, I get 1. 1 plus 2 is 3. If I put 0 in here and square it, I get 0, but I got to add 2. That's 2. You can see what's happening to the y values here is we just keep adding 2 to them. So I should just add 2 to that, call that 3, and add 2 to that, and call that 6. So 2 gets added to the y values. And what does that do to the graph? Well, now instead of over 2 and up 4, I'm up 6. So here, instead of over 1 and up 1, instead of over 1 and up 1, I'm over 1 and up 3. And instead of 0, 0, I'm now up 2. And I'm here, and I'm here. And so when I draw my graph, the graph moved up 2. Moved up 2. And that makes sense because all the y values are 2 more than what they used to be. And we could do another one here. Whoops. Y equals x squared. Let's go minus 3. And so when I square this, I get 4, but 4 minus 3 is 1. When I square negative 1, I get 1, but minus 3 is minus 2. And I continue to put in my table of values. And you can see that compared to the original one, all the y values are 3 less than these ones that we had in our original graph. And so now when I go over negative 2, I'm here at 1. When I go over negative 1, I'm at negative 2. 0 is minus 3. This one's at minus 2. And 2 is at 1. So these graphs look exactly the same. We haven't changed the shape here. They all look exactly the same. It's just we've moved everything down 3 here from our original graph. Everything's down 3. So moved down 3. So this number here at the end, this q, is a move up and down thing. So if you want to move your parabola, your original one, y equals x squared, up or down, that's what you're going to tack on to the end of the function. Positive is going to move it up, and negative is going to move it down. So if we've got our equation y equals x squared plus q, the value q is simply going to move the graph up or down. And if q is greater than 0, the graph's going to move up. So here q is 3, the graph moved up 3. And if q is less than 0, like y equals x squared minus 4, then the graph is going to move down. But the shape of the three graphs will remain exactly the same. We're just moving the graph up or down. That's what q does to the end of the function when you add or subtract a number to x squared. Now we have one last transformation that we can do to a function, and that is, what if we change the x value? What if we add or subtract something to the x value before we square it? So let's say I'm going to go, now usually we use the letter p to represent that change. So what if I make p 2? So we have x minus 2 squared. Well, let's do our table of values. We'll go with the same x values we've gone with here before. So if I put a negative 2 in here, negative 2 minus 2 is negative 4. Negative 4 squared would be 16. Now I'm going to put in negative 1. Negative 1 minus 2 is negative 3. Negative 3 squared is 9. And put in a 0. 0 minus 2 is minus 2. Minus 2 squared is 4. 1 for x. 1 minus 2 is minus 1. Squared is 1. Putting in a 2. 2 minus 2 is 0. 0 squared is 0. And I'm actually going to do a couple of more here. I'm going to put in a 3. 3 minus 2 is 1. 1 squared is 1. And put in a 4. 4 minus 2 is 2. 2 squared is 4. Okay, so minus 2, 16, I'm not even going to be able to draw because it's way off the screen here. But I can do, actually, let's get the original one on here just so we can compare. So this is the graph y equals x squared. There's our good old parabola. Y equals x squared. Okay, now let's draw this red one, this new one. So when we make the x minus 2, we couldn't plot that point, but we can do this one, I think. So when x is negative 1, y is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Fits up there. 0 is 4. 1, 2, 3, 4. 1 is 1. 2 is 0. 3 becomes 1. 4 becomes 4. So, connecting the points in a smooth curve. Wow, this looks like this whole graph has gone to the right. It's got the same shape, but everything has moved to the right too. This point went right too. This point's over here. This point's over here. Everything's right too. So replacing x with x minus 2 has moved the graph right 2. When we placed it, so I would assume that if we did this, x plus 2, oh, let's do that in a different color, blue. Negative 4 plus 2 is negative 2, squared is 4. Putting these values in, negative 3 plus 2 is negative 1, squared is 1, 0, 1, 4, 9, 16. That when we go to negative 4 and up 4, yep, negative 3 and up 1, negative 2, 0, negative 1, 1, 0, 1, 2, 3, 4, 1, 9. That when we connect these dots, we have seen that our graph got moved to the left 2. So when we replace x with x plus 2, then we move the graph to the left 2. So it looks like if you play around with the x and you replace x with something before you square it, you're going to end up moving the graph left or right. So if we have y equals x minus p squared, we know now that the value of p moves the graph left or right. And if p is greater than 0, the graph would move to the right p. So if I make p 4, I'd get x minus 4 squared, the graph would go to the right 4. And if p is less than 0, so if I make my p minus 7, I'd get x minus minus 7, which is x plus 7. So the graph would move left p. In this case, x plus 7, the graph moves left 7. So then just to summarize, we were asked to compare the graph of y equals negative 3x plus 2 squared plus 5 with the original graph y equals x squared. We would now know that this graph here would be reflected in x, because the negative sign is going to flip it upside down. So in other words, it'll open down instead of up. The 3 means that all y values are 3 times bigger, which is going to make the graph narrower. Then x minus 2 means the graph needs to be moved to the right 2, and then sticking a plus 5 on the graph is going to move the whole graph up 5. So these are the concepts behind the quadratic function, and in another video we'll look at how we can sketch the graphs of some of these things and do some analysis of complicated parabolas like this one.